In this video, I'd like to continue talking about complex numbers from their magnitude and their angle. Essentially, we need to find the complex number in its rectangular form with the real part plus the imaginary part, and we're given information about its polar form. So we need to know the formula for the polar form of complex numbers, which was derived in previous videos. But the complex number z1 can be rewritten as the magnitude of the complex number, its absolute value, multiplied by the cosine of the angle, plus I times by the sine of the angle. And if you have not seen where this comes from, I highly recommend watching the video on the polar form of complex numbers to see where this was derived from. Now, to convert this to rectangular form, and again, this is the polar form of a complex number, we just plug in what we know about it. We have that z1 is equal to its magnitude, which is 10, multiplied by the cosine of 84 degrees, plus I times the sine of 84 degrees, and we can distribute here. We have 10 times by the cosine of 84 plus I times 10 multiplied by the sine of 84. And at this point, we just need to evaluate these with a calculator and make sure your calculator is in degree mode and not radian mode. And we need to round A and B to the nearest thousandth. And this part right here, this will be a real part, A, and 10 times the cosine of 84 degrees is 1.045, and we will add the imaginary part, 10 times the sine of 84, all multiplied by I, and we get I times by 9.945, and I should be careful, we're really approximating at this point since we had to round, but this right here is our A value, and this right here is our B value. And there are ways to check this. For one, we can recalculate the magnitude, since the magnitude of a complex number is just the square root of the real part squared plus the imaginary part squared, essentially just using the Pythagorean theorem. And we can verify the angle from two different ways. We can use the formula for the angle, that theta is the inverse tangent of the imaginary part over the real part. Essentially, you draw a right triangle with this complex number and relate that angle theta to its opposite and adjacent sides, which are just the imaginary part and the real part. Or we can also just draw a quick sketch, since we found that this number is about at a real part of 1 and an imaginary part close to 10, so it should be somewhere right about here. And you can see that this angle would roughly be 84 degrees. So visually, it does make sense. But again, this is really just an approximate method for testing. To find the exact angle value, we need to use these formulas to verify that this makes sense. And keep in mind that if you do use this angle formula, you need to be careful if the angle is not in the first or the fourth quadrants. If it's in quadrant 2 or 3, you might have to add or subtract 180 degrees to make sense of that angle, since this formula is only valid or only gives outputs between negative 90 degrees and 90 degrees. So with this in mind, let's do one more example problem. And again, we will use that formula that z1 is the magnitude of the complex number multiplied by the cosine of the angle plus I times by the sine of the angle. And if we just plug in what we know, we have that the magnitude is 7 and the angle is 270. So we have the cosine of 270 plus I times by the sine of 270. Now, 270 is actually a special angle. If we use the unit circle, just a rough sketch, 270 degrees would be right here. And remember, on the unit circle, that this coordinate, so we're dealing with this angle, this is 270, this coordinate would have an x value of 0 and a y value of -1, but on the unit circle, the x values are the cosine values of the angle, and the y values are the sine values. And of course, if you don't remember this, you can always just plug these into your calculator to verify. But this right here is 0, and this right here is -1, meaning that z1 is 7 times 0. So that first part will cancel out, and we get 7 times I multiplied by -1. So this part goes away, and we get minus 7I as our final answer in rectangular form. But this makes sense because its magnitude would be 7. It is just 7 units straight down on the imaginary axis. And numbers that are on the negative imaginary axes, any number here, would have an angle of 270 degrees. So this does match up with the information we were given. We can use the formulas to verify that if we want, but this one is relatively straightforward.